Hello students, in this video we are going to continue our discussion on gravitation and we will be discussing the concept of gravitational field. See, every type of force has a field. Whether it is a magnetic force, it has a magnetic field. When you keep a magnet somewhere, right, so that magnet actually modifies the space around it, and the space around that magnet can actually experience the effect of that magnet, and that's why that space is known as magnetic field. The same way, when you place a charge somewhere, like you place an electric charge somewhere, it could be a positive charge, it could be a negative charge, so the space around that electric charge actually modifies due to the presence of the charge, and the effect of this charge can actually be felt in the space around that charge. So that space will be known as electric field. So we need to remember this, that the things, when they are kept in space, they actually modify the space around them. The same way you have a gravitational field. Okay, so how the gravitational field is going to be affected, that's what we have to see. What's a gravitational field? Suppose when you keep a mass somewhere, that mass actually modifies the space around it and the things get attracted towards that mass. Okay, but since gravitational field is not that stronger, so you need a very bigger mass to see the effect of that mass in the surroundings. For example, sun. Okay, so sun is something which bends the space. When it comes to the space, it is placed over there, it bends the space and everything actually gets attracted towards the sun. I'm going to share a video in a link where you will be viewing a simple activity which will show you that if you keep a cloth, okay, on a well tighted cloth on a container, okay, had it been placed no ball over there, then you're going to face no gravity there. But when you'll actually place a ball over that cloth, that will produce a dent in that cloth. And when you put another small ball over there, it will start rotating around that bigger ball placed over a cloth. That is happening because that bigger ball is actually bending the space. It is creating a dent in the space, reason being because of its mass. So that's gravitational field actually. That mass attracts the another masses in a space, in a region, and that region is known as gravitational field. So topic number 1, intensity of gravitational field. How to measure the intensity of a gravitational field at a certain point. Suppose you have a mass capital M over here. Due to this mass, the space around this mass is feeling the gravitational attraction because of this bigger mass. So if you want to measure the effect of gravitational force due to this mass at some point P, suppose you keep a unit mass there. Now with what force that unit mass is getting attracted towards this bigger mass, that will decide what is the intensity of gravitational field at that point. Like farther the point, lesser will be the intensity of gravitational field at that point. For example, talking about sun, the planets that are nearer to sun experience stronger gravitational pull. The planets that are farther from sun, they experience lesser intensity of gravitational field due to sun. So yes, remember that intensity of gravitational field at a certain point, how can we check it? Okay, see, if you want to check the intensity of magnetic field, there is a magnet and you can only bring another magnet. And you have to see how strongly another magnet is attracted or repelled by the first magnet. Okay, same way, when you see a charge, when you want to measure the intensity of electric charge and you have kept a charge over here, then you need to keep a very, very smaller charge there to experience the electric field due to this bigger charge. If that smaller charge is going to be attracted or repelled, that will tell you what is the intensity of electric field at that point. मतलब आपको अगर किसी भी field की intensity check करनी है ना, तो आपको same nature की things को लाना पड़ेगा. जैसे मुझे mass की वजह से gravitational field जो आ रही है उसकी intensity check करनी है, तो मुझे वहाँ पे एक mass को ही रखना पड़ेगा. And I would have to see कि कितने force से वो mass attract हो रहा है. I hope you are understanding this. So, what will be the force of gravitation over there? Suppose instead of keeping a unit mass, you are keeping a very, very smaller mass called m naught there. Okay, the force of gravitation between them will be written as gm, second mass m naught, upon the distance between the two masses. Let us suppose it is x square. Okay, now intensity of gravitational field says that what will be the force experienced by unit mass. So if m naught mass is experiencing this much force, by applying unitary method you can find out the intensity, which is force experienced by unit mass. Divided by the mass, you will get the force. This will become gm by x square, and this is intensity of gravitational field. Remember, intensity of a gravitational field is a vector quantity. It has a direction also. So this goes as I vector equals to minus gm upon x square, x cap. Okay. Why we have used the minus sign here? Because the force is attractive. That is why. X cap is the distance from this mass to this mass. It's a direction from this mass to this mass. Okay. So x cap is a vector quantity. I vector is a vector quantity. These two vector things are related by a negative sign because they have opposite direction. Okay. You better know this, that every vector quantity, A vector, is written as magnitude of A and A cap, direction of A. So same way intensity vector, A की जगह I vector equals to magnitude. Magnitude की value है gm by x square और multiplied by direction. Direction x cap के opposite है. x cap direction है m से m naught तक. लेकिन जो भी intensity of gravitational field है, see that this mass is getting attracted towards this side because this is a smaller mass. I told you, when you want to check, you bring a tester there, and that tester is a smaller magnitude. So this is the direction of intensity. So that's what I have done over here. And this whole topic is intensity of gravitational field. So you got to know that I is equal to gm upon x square. Suppose x is equal to infinity, like this is the bigger mass and the smaller mass is kept at an infinite distance from that bigger mass. So if x is equal to infinity, the equation will become I is equal to gm into 1 by infinity, and 1 by infinity is nothing but 0. So this means intensity of gravitational field is 0 at infinite distances only. Okay. Also, I is equal to gm by x square, right? This force is equal to m naught into A. Okay. F upon m naught is equal to A, acceleration, and intensity was said, we said that intensity is equal to force experienced by per unit mass. Force experienced per unit mass. So basically F upon m naught is equal to A also, and F upon m naught is equal to I also. So intensity is basically telling you the acceleration. Okay, intensity of gravitational field is basically telling you the acceleration with which the unit mass is getting attracted towards the bigger mass, right? So what will be the unit of intensity? If you take the formula F by m naught, it is newtons per kg, right? And if you take acceleration, that intensity is equal to acceleration. So this becomes meters per second square, but this is one and the same thing, right? Now talking about the dimensional formula, how to go about it. See, intensity is equals to force upon m naught, right? So force, dimensional formula of force is mlt minus 2, and the dimensional formula of mass is m. So this m gets cancelled with m and you're going to get m0 L1 T minus 2, right? So now let's switch to the next topic, which is gravitational potential. Just you have studied about electric potential, magnetic potential. So what is a gravitational potential? So let's understand this. Suppose you have a bigger mass here, right? And the value of that mass is capital M, okay? And you are bringing a unit mass from infinite distance to a particular point. Then what will be the work done in doing that? That will decide the gravitational potential at that point. Okay, I repeat, if you want to measure the gravitational potential at a particular point, so this is a bigger mass, okay, it is exerting a gravitational pull in all its surroundings. And we have selected a point where we want to measure the gravitational potential. So what we need to do, we just need to bring an unit mass from infinity to that particular point, and the work done in doing that is actually equal to gravitational potential, and the things go like that. So yes, this is gravitational potential. Let me write it P. Let me denote it with P, and this P will be equal to work done per unit mass. Okay. So its SI unit is joules per kg since it's work done per unit mass. Work done is measured in joules, mass is measured in kgs, and that's why we are going to get it joules per kgs. And when you switch to the CGS unit, it has to go like work done is measured in ergs and mass is measured in grams. So ergs per grams is the unit of CGS unit of gravitational potential. It's a scalar quantity since a work done is the scalar quantity, right? So then you can find out the dimensional formula also. Now let us find out the expression for gravitational potential. How to go about it? Suppose you have a body here, okay, it is its center, right? And this body has mass capital M. And now you are bringing a unit mass from infinity to a particular point called P, which means you have to measure the gravitational potential at point P. I repeat, you have an object here whose mass is capital M, and because of its mass, there is a strong gravitational pull in the surroundings. And I have to measure the gravitational potential at a particular point P. And to do that, what I'll be doing, I'll be bringing a unit mass from infinity to this particular point. The work done by me will decide the gravitational potential at this point itself. So how to go about it? Suppose the distance from this body to the point P, that's R, okay? And when I'm bringing the unit mass from infinity to this point P, I will encounter two more points here in the path. First will be A and the second one will be B. So I'll calculate the small amount of work done in bringing the mass from A to B, and then I'll integrate the whole work done to get it towards the P. It's as simple as that. So when you're bringing a unit mass, what will be the force of gravitation between that unit mass and this body of mass capital M? See, by Newton's law of gravitation, you know that force is given by gmm upon x square, right? But since the other mass is a unit mass, so in place of small m, you can of course write 1, right? So F becomes equal to gm by x square. It's as simple as that. After that, find out the work done in bringing that unit mass from A to B. So that will be dW equals to F dx. The force of gravitation is also, see, otherwise the work done is equal to F vector dot dx vector. Is it true? And when you open that dot product, this becomes F dx cos theta. F dx cos theta. Theta is the angle between force and the displacement. Now the gravitational force is attracting the object towards itself. So this is the direction of force, right? And this is the direction of displacement also. So this means force and displacement are sharing an angle of 0 degree with each other, right? So in place of theta, you're going to put 0 degree. So this will become f dx cos 0 degree, and cos 0 degree is nothing but equal to 1. So this will become f dx, and f dx, put the value of f gm upon x square into dx. So this is the small amount of work done in bringing the unit mass from A to B. Now we have to find out the total work done. So total work done can be calculated because we are shifting the mass from infinity to a point whose distance is r, right? So work done will become, so the work done becomes integration within the limits infinity to the point P whose distance is r. See, infinity is the distance of the infinite point from O, okay? So let us integrate this equation gm by x square dx. I'll tell you a rule of integration now. The rule says that if the integration is to be done with respect to a certain variable, for example, if I want to integrate x raised to the power n dx, the integration has to be carried out with the variable x, and this is a power rule of integration, x raised to the power n dx. The rule says that the integral will become x raised to the power n plus 1 divided by n plus 1 plus constant. Okay, so if there are no limits, then this constant appears in the solution. But when there are limits, then this constant does not appear in the solution. So that way, what are we going to do? We have gm as constant taken outside the integral, limits infinity to r, and this 1 upon x square can be written as x raised to the power minus 2, this dx as it is. Now we are going to apply the same power rule over here. In place of n, you can see minus 2 here. So x raised to the power minus 2 dx. Rule says wherever you are seeing n, put minus 2 there. And when you do that, you're going to get this solution. I repeat, when there are limits to the integral, then the constant will not appear. These limits will be taken as it is. Okay, infinity to r. Whereas when you see no limits, then the constant has to appear. So this gm remains constant here. X raised to the power minus 2 plus 1. I've just applied this rule. Minus 2 plus 1 is minus 1. Again, minus 2 plus 1 is minus 1. Take this minus outside. So this becomes w is equal to minus gm. And this x minus 1 can be written as 1 upon x. And the limits are infinity to r. Now, how to solve these limits? Wherever you are seeing x, put these limits. Okay? And the solution has to go like upper limit minus lower limit. So this will become 1 upon r minus 1 upon infinity, right? So 1 upon infinity is 0. So 1 upon r is left with minus gm. So work done will become minus gm upon r. So this is the work done in carrying a unit mass. See, we considered unit mass, right? So we considered unit mass. So this is the work done minus gm upon r in carrying a unit mass from infinity to the point whose distance from the mass capital M is r. Okay, so this way the derivation has to go. Now we'll talk about gravitational potential energy. This was the expression of gravitational potential. Let us now talk about gravitational potential energy. Now, what is gravitational potential energy? In gravitational potential energy, we will not consider a unit mass. We'll simply consider that if there is a mass capital M, whose gravitational field is extending to a space, and in that space, you are bringing a mass which is not a unit mass, you are bringing a mass of small m to a particular point, then what will be the work done? The derivation is exactly the same. It's just that we are not going to consider unit mass over here. We will not say that we are finding out work done per unit mass. That is gravitational potential. Here we will say what is the work done in bringing a mass of m, small m, to the mass of capital M. So exactly the derivation is same. Again, the dW will be equal to F dx. Okay, but here force will not be taken with respect to unit mass. Here the formula will go like gmm upon x square. All the steps are same. It's just that in place of 1, small m will appear. And ultimately you are going to get W is equal to minus gmm upon R. Okay, so this is gravitational potential energy.